Right. So last class we talked about the first chi-square test, right? So let's review a little bit. We say we want to test whether the distribution of the trading days will fit. We have the model of the trading days, whether this model will fit the distribution of the updates, right? So then we say we have one categorical variable, the days of the week, and then with this categorical variable, we have 1, 2, 3, 4, 5 categories, right? And then we have their corresponding counts. How many of them belongs to this category? How many of them belongs to this category, right? And then we can calculate their corresponding percentage, and we say we want to know whether the distribution of the trading days will fit the updates, right? And then we say we can go through a chi-square goodness of fit test to test whether the model fits our sample data about the updates, right? And then we say before we calculate the test statistics in the second step, we need to check these four assumptions, right? We need to make sure our data is counted data, right? We have how many of them belongs to each category. We need to make sure these counts are independent of each other. We also need to make sure the sample is randomly selected. And the last one, we need to make sure we have enough sample size, right? We need to make sure every account should be larger or equals to 5. Right? Then we say once these four assumptions are all satisfied, then we can calculate, we call the chi-square test statistics by this formula. Right? And then we say for each observed count, we need to calculate their corresponding expected counts, right? And then we need to calculate for each pair of observed and expected counts we have to calculate the observed minus the expected squared divided by the expected, right? And then in this case, we totally have how many counts? We have totally 5 counts, right? We also call them our cells. So actually we have 5 cells. That means we have 5 observed counts, right? So actually these ones are from the sample we selected, right? So we call these counts are the observed counts, right? And then how to find the expected counts? We say expected counts will be without the details of this sample. I know the total number of sample observations is 1,110 observations in this sample. Right now, without the details of this sample, how many of these updates you expect to be on Monday, right? So how you can get the expected counts for Monday? That means you use this model to percentage for the Monday, right? So that will be 1,110 times the corresponding 19.305%, right? So that means generally we use the sample size, the total sample size, times the percentage in the model to get the expected counts, right? So that means we can get the expected counts for Monday, for Tuesday, for Wednesday, for Thursday, and Fridays. And then that means this column, we can calculate it as n times the percentage in the model. And then for each pair, for each cell, you calculate the observed minus the expected squared divided by the expected, so that you have 5 values for each cell, right? And then the last step, sum together to get your chi-square test statistics, right? And then we say once we calculate this chi-square test statistics, we can go to the next step. We want to find the p-value based on our chi-square test statistics, right? So that means we need to go to the chi-square table, right? And then before we calculate or before we find the p-value, we need to fix our degree of freedom line, right? So for the goodness of fit test, the degree of freedom is number of cells minus 1. So here be careful, it is not n minus 1. It is not n minus 1. It is number of cells minus 1. So number of categories or number of counts. Right, so we have 5 counts here. We have 5 categories here, or we say we have 5 cells. All right, so that means the degree of freedom will be 5 minus 1. So the degree of freedom in our example is 4. Right, and then we just focus on this line and see, okay, my chi-square test statistics, right, made between these two values, and then you just go up to find the range of your p-value. Right, and then we say once we have the range of the p-value, when we compare with the given significance level alpha, right, then we say if the p-value is less than alpha, we reject the null hypothesis. Right, so I would suggest you to think about or come back to our hypothesis. Right, so remember our null hypothesis is the model fits the data we selected. Right? Alternative hypothesis is the model doesn't fit our sample data. Right? So that means if we reject the null hypothesis, that means we have enough evidence to support that the model doesn't fit the sample data. Right? Then the other way, if the p-value is larger than the significance level alpha, then we fail to reject the null hypothesis. We do not have enough evidence to support our alternative hypothesis. Right? Okay, so that would be our first chi-square test. Right? We call it is the goodness of fit test. Right? We want to know whether it is a good fit from the model to our sample data. Right? We call it is goodness of fit test. All right, next for today, we'll talk about another kind of chi-square test. Right, we call it is the independence test. Right, so when we talk about the independence, we talk about at least two things, right? We want to know whether there is any relationship between these two, or whether these two are independent of each other. So that means for the test of the independence, we have at least two categorical variables. Right, so to compare with the goodness of fit test, we only have one categorical variable in the goodness of fit test, right? But for the independence test, we want to test the relationship between the two categorical variables. That means we have at least two variables. Let's say more specific. Say we have two categorical variables. Right? So that we have one categorical variable, the other categorical variable. Right? And then we want to know whether these two categorical variables are independent or not independent. They are related or not related. All right. So before we go through this independence test, right, again, we go through this example first. Right? So this is a Titanic survival summary, or actually summary of the sample. All right, so in this table, we call this is a two-way table. It is not a simple table, it is called a two-way table. Why it is called two-way table? We have one direction, the other direction. Right? We say the first direction, the horizontal direction is actually the categories of one categorical variable. The other direction, the y direction, shows you the categories of another categorical variable, right? So that means for here, I have two categorical variables. The first one, the crew first, second, and third are the classes of the passengers on the ship. Right, so this is the first variable, and for this variable we have 1, 2, 3, 4, 4 categories. Is that right? Okay, and then we have another categorical variable in this table. We have what? We have alive or dead, right? So actually, is their survival status. Right, and then for this categorical variable, we have two categories, alive or dead, right? So that means I have two categories in this categorical variable, right? So that means in this table, we combined these two categorical variables together as one table. And then we call this is a two-way table. All right, and then before we go through the hypothesis test steps, we want to learn something about this two-way table. Right, so first, generally, for any two-way table, we have a main part of the two-way table. We call this is the main part of the two-way table. In this two-way table, we just show the counts for each combination of the two categorical variables, right? So for example, what is this 212? What is this 212? What does that mean? When you read this table, what does that mean? Thomas?
Out of the crew that were on there, only 212 were alive.
Yes, perfect. Right, that works. Right. So actually this 212, that means there are 212 passengers are in crew and stayed alive, right? So actually this 212, this count is the count of the combination of two levels in these two categorical variables, right? And then we have how many of them? We actually have 8 of them. Right? How you get this 8 of them? So actually we have 4 levels for this variable, for two categories for this variable. Then we totally have 4 times 2, which is 8 combined levels. Right? Then we call this is the main part of the two-way table. Right, why we call it is the main part. Normally, when you see a two-way table, you have some extra, you have one more row, one more column, which are the totals. Right? So these totals are calculated from the mean part of this two-way table. They are not the real table. They are not the real two-way table, right? But normally we need to use this row or this column for calculations, right? Then we call these counts, right? We totally have 8 counts, 8 combinations, right? Then we call these counts are the cells, right? Then actually they are the observed counts, right? We call they are the 8 cells, all right? And then for the totals, we say for this 885, we call this is the marginal total. Right, so that means this 885 is calculated by sum up of these two counts in the crew class, right? Then we call it is the marginal total of crew class, right? And then this 325, this is the marginal total of first class. Right? Similarly, we have 285 as the marginal total of the second class. Right? This is the 706, which is the marginal total of the third class. Right? And then here we have one more column is also for the totals, and this total is what? This 710 is the total of these counts. Right? So actually this is the total for all alive cases. Right? So then we call this 710 is still the marginal total for alive. Right? And then next, 1,491 is the marginal total for dead. Right? To be different, to just make a little bit difference, we also call these ones, right? So these green ones are the marginal totals calculated in this direction, right? Then we call these totals are the column totals. Right? And then this 710, and also this 1,491, these are calculated in this horizontal direction. Then we call this two are the row totals. Right? These ones are the column totals. All right, and then only one left. Right? So we only have one left. We call this 2,201. What is this? This is the sum of all these 8 cells. Right? And also you can calculate this total as the sum of these 2 row totals or sum of these 4 column totals. Right? You will get exactly the same total. So we call this total as the overall total. All right, so kind of a mess here, right? So let's say one by one. All right, we say for the main part of the two-way table, we have the detailed counts for each combination of the two levels for the two categorical variable. Right, so we have the mean part, and then in each mean part we have we call each part or each count as one cell, so that we have 4 levels for one variable, 2 levels for the other categorical variable, and then 4 times 2 will be 8 cells. Right, so in the mean part of the two-way table we have 8 cells. All right, and then we say we normally add one more row for the column totals. We have one more row for the row totals, right? So for the column totals and row totals, we both call them our marginal totals, right? So since this 885 is calculated based on this direction, right? The column direction, then this is called the column total, right? The marginal total for the crew. And then this one is also the column total for first class, right? It is also called the marginal total for the first class. Right, next one, the marginal total for the second class, the marginal total for the third class. Right, and then the only one left on the corner, right corner, which is our overall total, right? So this 2001, 2,201 is the overall total. All right, so we kind of got the general idea about this two-way table, right? So with this two-way table, you need to understand what does each entry mean. All right, and then we can go through this hypothesis test now. Right, so again, first step, state the hypothesis. right? So again, since we are testing about whether these two variables are independent of each other or not independent of each other, then your hypothesis will be simple. The null hypothesis is they are independent, right? The alternative hypothesis will be the variables are not independent. Right, so the null hypothesis is they are independent. Alternative hypothesis, they are not independent. Right, and then second step, to calculate the test statistics, we say before we use the formulas, we need to check the assumptions. Right, so now let's come back to our goodness of fit test. We say for goodness of fit test, we have 4 assumptions. Right, so we need to check whether the data is counted data. We say for chi-square test, the chi-square test only can take care of the counted data. So this is always the first assumption you need to check for any chi-square test. So that means for independence test, we also need to check this assumption. We also need to make sure your data is counted data. All right, and then next one, we still need to make sure the sample is randomly selected. Right, we still need to make sure for each cell you have enough sample size. For each cell, we need to make sure the count is larger equals to 5. Right, the only one different is the second assumption, the independence assumption. Do we need to check the independence assumption for this test? Of course not. Right? We do not check the independence assumption because we are testing about it. Right? We don't know whether they are independent of each other or not. Right? So we do not check the independence assumption in the independence test. Right? So this is our goal. We will make this conclusion at the end of this test. So before we do anything, we don't know whether they are independent or not. Right? So for the independence assumption, we only have these 3. Right? We do not have independence assumption anymore. All right, so be careful here. Right, now we have these 3 assumptions checked. Right, we still need to make sure the data is counted data, the data is randomly selected, and for each cell should be at least 5 individuals. So again, each cell, how many cells we have? We only have 8 cells. Right, not 15. Be careful here, right? So we only care about the mean two-way table. This total row or total column, they are just just try to help us to solve other information, right? Okay, so we say for each cell, we need to make sure it is at least 5. Right, so we say after we check these 3 assumptions, only when these 3 assumptions are all satisfied, we can continue to calculate this chi-square test statistics by this formula. Right, so formula didn't change. The formula is the same with the goodness of fit test, but the point is, say we still need to get the observed counts. We need to get their corresponding expected counts, and then for each pair we need to get the observed minus the expected squared divided by the expected. Right? Okay, so now what are the observed counts in our example here? What do you observe from your sample? That will be the counts, this one, right? This one, this one, this one, this one, this one, this one, this one will be the counts in our totally 8 cells, right? So that will be our observed, that will be our observed counts, right? So it would be 212, 202, 118, 178, and then 673 until the last one, which is 528. Right, so these ones are our observed counts. Right, next, how to get our expected counts. Right, so the expected counts will be calculated by this formula. We say the expected of ij will equals to total row I times total column j divided by table total. So what does that mean? So let's look at more details for this example. Right, so let's just look at this first one, for example. Right, we say this 212 is the counts for the combination of these two levels, crew and alive. Right, so what is the location for this count? It is located in the row number 1, column number 1, right? And then we call this 212 as the observed count for row number 1, column number 1, so that we can write as the observed count for 1, 1 equals to 212. Right, so this 11, this is not 11, this is 1, 1, tells you what is the location for this cell. Right, so more generally, we say the observed count for ij. So this I will tell you which row this cell belongs to. All right, this j will tell you which column it belongs to. Right, so if I write as observed count for 2, 3, what is the value of observed count for 2, 3? Which one? Anyone can answer this question? What is the count for observed count for 2, 3? Be row number 2 combined with column 3, right? So row number 2 combined with columns 3, so it would be this 167. Right, so this 2 and 3 tells you the location of this observed count. Right, so this is, let's say, one more example for this 528. What is this? How to write the notation for this count for this 528? Garrett, are you there? Garrett?
Did you say Grant?
Oh, it's fine. All right, Grant. Yeah.
Okay. Is that 2, 4?
2, 4, right? So we call it is observed count of 2, 4, which is the second row combined with the fourth column, right? Perfect. Good. All right, so now we figure out what does this ij mean. It is the location of this cell. All right, now let's erase that. And then this is the observed count. And then I want to know what is the expected count for this cell. By the formula, it's equals to expected count for ij. Now we are focusing on 1, 1, right? So this is our first one, right? So that means by the formula, it will be the total of row 1 times total of column 1 divided by the overall total, right? So now let's come back to our table. So what is the expected count for this first cell? It will be the row total, which is 710 times the column total, which is this 885, divided by the overall total, which is this 2201. Right, so that means for the first cell, the expected count will be 710 times this 885 divided by the overall total, which is 2201. Right, so it belongs to row number 1, so you use the row number 1 total. Right, so it belongs to this row, so you use the row total of this cell, and then times the column total of this cell divided by the overall total of this table. Got it? All right, let's try one more. Let's say this 1, 2, 3. Right, so this is the observed count. So what is the expected count for this cell? It belongs to this row, right? So we use the row total times the corresponding column total divided by the overall total, right? So that means the expected count for this cell will be 1491 times the column total is 325 divided by the overall total 2201. So then this is the expected counts for this cell, so that you have the observed count, which is 123. You have the expected count is this many, right? And then you use the observed minus the expected squared divided by the expected in the formula, right? So now let's try one more. Say it's your turn. All right, so it would be 178. So we'll say 178 is the observed count for this cell, right? Then what is the expected count for this cell? Let's say Austin. What is the expected count for this 178 for this cell?
What is the expected count?
Mm-hmm.
I'm not sure.
Not sure, it would be the row total times the column total divided by the overall total. Think about it. What is the row total for this cell?
7. Oh, is it only 178? Or is it 710?
It would be, okay, so this 178 is the count for this cell, right? And then we use, it belongs to this row, then we use the row total. Right, so it will be 710 times the column total. It belongs to which column? It belongs to
Column
the
3.
right, so it will be the third, not the third, which belongs to the third class column, right? Then times the column total, which is this 706, divided by the overall total, which is 2201. Got it? All right, row total times the column total divided by the overall total. Right, now let's try one more. Make sure you understand what does that mean. All right, so one more. What about this 167? What will be the expected count for this cell?
Can I ask a question really quick?
Sure.
Are we gonna be like given an expected?
No, you need to calculate the expected count by yourself.
Well, are we supposed to do this for every single cell, or are we gonna be told which one to calculate?
You are required to calculate for every cell. So you need to
And
calculate this expected count for every cell of these 8 cells.
okay. And then do you add them all up or something?
We will talk about this later.
Okay.
Right, so now we just focus on how to get the expected value or expected count for each cell. Right, good question. Right, let's say Julia. Right, so how you can calculate the expected count for this 167 cell?
It would be 1491 times 285 divided by 2201.
Perfect, good job. All right, so now you understand how you get the expected counts. Right, now let's come back. We say we have their observed counts, right? And then based on the location where it belongs to, right? So 212, it belongs to this first row and first column, so that we can calculate the row total times the column total divided by the overall total to get their expected counts, right? So actually we can fill this column from this table, right? Calculate as the row total times the column total divided by the overall total, right? To calculate these expected totals, right? Expected counts, right? And then based on your observed counts and your expected counts, you calculate the observed minus the expected squared divided by the expected to calculate the value for each cell, right? So remember, in our example, we have totally 8 cells. That means you need to calculate this 8 times, right? And then last step, remember in the chi-square test statistics formula, you have the chi-square test statistics to be sum of these together, right? Then you will have the chi-square test statistics. Right, so there will not be any problem to find the observed counts because they are just listed in your table, right? The expected counts will based on the location of your cell, right? So if it is located in the first row and first column, then you use the row total times the column total divided by the overall total to get the expected counts. Right, so once you get the expected counts, then you can use the observed minus the expected squared divided by the expected to calculate this term for every cell. And then remember the last step for the chi-square test statistics is to sum of all the cells you have. So you need to sum of all of these together to get your chi-square test statistics. Right. The whole idea is exactly the same. The only thing different is the way how you find the expected counts. All right. So now once we have the chi-square test statistics calculated, then the next step will be find the p-value again, right? So we go to the chi-square table. We need to fix the line of the degree of freedom and then find the chi-square test statistics is between 2 values, and then you go up to find the range of your p-value. Right? So the process here is exactly the same. The only difference is you have another degree of freedom. right? So you have another degree of freedom for the independence test. We say for the goodness of fit test, the degree of freedom is equals to number of cells minus 1. Right, so now for the independence test, the degree of freedom equals to number of rows minus 1 times number of columns minus 1. Right, now let's come back to our example. So what is our degree of freedom in our example? Right, so we need to fill how many rows do we have? Do we have 3 rows or 2 rows? Anyone? We have 2 rows or 3 rows?
We have 2 rows.
2 rows. Perfect. Right, so this total is not the row we care about, right? We care about the mean two-way table. Perfect. How many columns do we have? Chloe, how many columns do we have?
4.
4, right? Perfect. Good job. Right, so we do not have these 5 columns. Actually, this is our main table. We don't care about this actual column, about total, right? So we have only 4 columns. In the end, we say 2 minus 1 is 1 times 4 minus 1 is 3, so that our degree of freedom 3. Right, got it? All right, so once we have the degree of freedoms 3, and then we go to the line of 3 and find our chi-square test statistics between 2 values, go up to find the range of the p-value. All right, so once we have the range of the p-value, again, we make the conclusion based on comparing to the significance level alpha. Right, so again, we say when we make the conclusion, we always need to go back to our hypothesis. Right, so our null hypothesis, they are independent, right? Alternative hypothesis, not independent. Right, now if the p-value is less than the given significance level, that means we reject the null hypothesis, right? Not yet. Reject the null hypothesis, that means we have enough evidence to support our alternative hypothesis, which means these 2 variables are not independent. Right? So the other way, if the p-value is larger than alpha, then we fail to reject the null hypothesis. That means we do not have enough evidence to say they are not independent. Right? So we don't have enough evidence to support our claim. Right? So we have 2 nots. That means what? That means they are independent. Right, we fail to reject the null hypothesis. That means the null hypothesis is supported. All right, okay, so now let's go through this example, right? We keep working on this example, right? So now we go through these 4 steps one by one to make everything organized. Right, so we say we want to test whether these 2 variables, which is the classes on the shape and their survival status, right? Well, I want to know whether these 2 variables are independent or not independent. Right, so the step 1, state the hypothesis. You can either say the variables are independent, the variables are not independent in this way, or you can state it in more details, right? It's your choice. Right, so if you state in the detailed hypothesis, it will help you when you make the conclusion, right? You don't need to try to think about what are these 2 variables, right? So it depends on you, right? I will prefer this way, right? Okay. Then next step, right? Before we calculate the test statistics, we need to check 3 assumptions. remember it's 3 assumptions, not 4 assumptions anymore, right? We do not check the independence assumption anymore, right? We check whether our data is a counted data, right? Whether our sample is randomly selected, whether our sample size is large enough. That means for each count, for each cell we have, it should be larger equals to 5. Right, so that would be our assumptions, right? So we say all of these 3 assumptions are all checked. Then we need to calculate our test statistics, right? So I think this is the most complex part in the whole, maybe not a whole semester. One of the 2 hardest calculations in this semester, right? So you need to be very careful when you make this calculation. All right, so we say to calculate the chi-square test statistics, I will suggest you to always give the 3 columns, right? So we have the observed column, the expected counts column, and then we have the observed minus the expected squared divided by expected, right? So you better to list them out so that you don't get confused. All right, and then we say based on the given table, right? Based on this given table, we can list all of these observed counts, right? How many of them? How many observed counts? We just focus on our main table, right? Which is totally 8 of them, right? 212, 202 until 528, right? So we just list them out, right? And then we need to calculate the expected count for each cell, right? So first, for the first one, we have already talked about, right? So for the first one, 212, what will be the expected count for this cell? It will be the row total 710, right? Times the column total, which is 885, divided by the overall total 2201. Right, so that will be after your calculation, you have your expected count is 285.48. Right, and then next step, you need to calculate the corresponding observed minus the expected squared divided by expected. Right, so it will be what? It will be 212, the observed minus the corresponding expected 285.48. Then squared divided by the expected 285.48. Right, so that will be this 18.91. Right, then you need to repeat the whole process for number of cells times, right? So you have 8 cells, that means you need to repeat the whole process for 8 times so that you can calculate this part, this formula for 8 cells. And then to get the chi-square test statistics, you need to sum of all of these cells together. Right, so these ones are the observed minus the expected squared divided by the expected counts. Right, remember our chi-square test statistics is the summation of all cells. For each cell, you need to calculate this term. Right, so that means you need to sum of all of these items together to get your chi-square test statistics. All right, so this is a long calculation process. All right, and then once you have your chi-square test statistics, everything just be easy. Right, so we say once we have our chi-square test statistics, it is 187.78, right? And then we find the p-value based on our test statistics. We need to go to our chi-square table. And then before that, we need to fix our degree of freedom, right? So we have already talked about the number of rows, which is 2 minus 1, times the number of columns, which is 4 minus 1, right? So that means the degree of freedom will be 1 times 3, which is 3. Right, so now let's go to our chi-square table. Right, we say our degree of freedom is 3. 3. Right, and then we have our chi-square test statistics calculated as 187.78. Right, so now what is your p-value? Our degree of freedom is 3, so that means we focus on this line, right? And then based on our test statistics, 187.78, what is your p-value? Johnny, what will be your p-value?
Wouldn't your p-value just be less than 0.005 then?
Perfect, good job. All right, so that means your chi-square test statistics 187.78 is to the right of the largest one, which is 12.838, right? So that means your p-value will be to the right of this 0.005, right? So it will be larger than this 0.005 or less than this 0.005. Let's see the trend, right? So if we are going through this direction, the value is getting smaller and smaller, right? So that means your p-value should be smaller than this 0.005. All right, so now we got the range of the p-value. We say the p-value is less than 0.005. Now, if the alpha is given to be 0.001, that means this 0.005 is less than 0.01, right? So this is your alpha. That means your p-value is less than alpha. That means we reject the null hypothesis. Remember what is our hypothesis? They are independent. They are not independent, right? So now we reject the null hypothesis. That means we have enough evidence to say these two variables are not independent. So which two variables, right? You need to specify. They are the survival status and the classes on the ship, right? These two variables are not independent. Right, so when we say, excuse me, yes.
May I ask a quick question? I thought we had 8 cells, so I'm not getting why the degree of freedom is 3.
Oh, okay. I think you missed this one, right? We say the degree of freedom equals to number of cells minus 1. This is the degree of freedom for goodness of fit test.
Oh, okay.
Right, for our test, for this independence test, the degree of freedom equals to number of rows minus 1 times number of columns minus 1. So how many rows do we have? 2 rows, right? Minus 1 times how many columns do we have? We have 4 columns, so 4 minus 1. So that will be 3. Got it?
Okay, thank you.
You're welcome. All right. So then we say these two variables are not independent, right? Sometimes someone may make the conclusion about since they are not independent, that means what? That means they are related, right? So don't get confused. If they are not independent, that means they are related. There is some relationship between these two variables. All right. Any questions? Any question? Good. All right, so the last part, of course, I will talk about how to get this hypothesis test done by the jump. Right. So now you know what is going on inside. Right, now let's go through the jump. Right, so the jump doesn't provide the function for the goodness of fit test. So I will just show you how to do the independence test. Right, so let's just use this Titanic example. Right. So we say we want to make a hypothesis test, or we want to make any data analysis about your data, right? Then you need to enter your data into the data table so that we can analyze it, right? But now we have a table, so how we can enter this table into the data table, right? Then we say we need to convert the format from the two-way table to the regular format of a data table, right? We say the data table, the top line should be the variables, right? But now we have two variables. We have their survival status and their classes, right? And then we have their corresponding counts. So that means when we want to enter this 212, this count into the data table, we need to specify which level does this count belongs to, right? So actually this count, it belongs to the crew class combined with the alive level, right? So that means it will be alive for the survival. Right, so it will be the alive for survival, and at the same time combined with the crew class, right, with the counts 212. Right, for example, next one, 202. When you enter this count into the data, this is the combination of alive and first class. Right, so that I can enter A for alive and F for the first. You can also just enter the full name of it. I just use the F for short. Right, similarly, you have the alive for the second class, alive for the third class, and then that will be the four counts in the first row. Right? And then for the second row, similarly, you have the dad combined with crew, the dad combined with the first class, right? So the dad with crew, dad with first class, dad with second class, dad with the third class. And then you just enter their corresponding counts, right? That will be the data table you can use to make the hypothesis test. Right, so once we enter all of our counts into the data table, we do not need to enter the totals, right? The jump will calculate the totals for us, right? So then we need to analyze it, right? So when you click the analyze, normally we will use the distribution function, right? But remember, if you put the arrow on the distribution function, it will tell you that this function is used to display a histogram and univariate statistics for what? For each variable. Right? So that means this function works for only single variable. That means it doesn't work for our case. Our case, we have two variables. We want to know the relationship between these two variables, right? And then we need to go to the next function, right? If you put the arrow on this function, it tells you that if you use this function will tell you the models, it will models the relationship between the two variables. Right, so now we use the fit y by x. So we have two variables, y and x. Right, okay, and then in this screen, we need to pull the variable's name into different spaces. Right, so we say the counts. What are the counts? The counts will be how many of them belongs to this combination of the levels, right? So actually the counts are the frequencies, right? So we just pull the counts to the frequencies. All right, and then we have two more left, right? One is the survival. If we want to follow the same format here, that means the survival levels are the columns, right? Will be the Y direction, right? So then we can use the survival goes to, no, not survival, the classes, right? So the classes are in the columns, right? So actually the classes will be the Y, and then the alive or dead, which is the survival status, are the rows, so which is the X. All right, and then click OK. Right, so this is the default outputs we have. Right, the first one, it give you what? Give you a mosaic plot. We will talk about this plot in the end of this semester. Right, so actually this mosaic plot tells you the distribution within each category of this categorical variable. Right, so for example, for the survival status for this categorical variable, right, we have two categories. Right? So we have alive or dead. And then we say within alive category, right? How does these classes distribute it? Right? We can say that, okay, it looks like the red is the crew class, right? F is the first class. So in the alive category, right, kind of the crew and the first class kind of have the same proportion or the percentage of the passengers, right? And then next one will be the third class will be more alive than the second class, right? So based on this mosaic plot, you kind of get the pattern within each category of this categorical variable, right? So we'll talk about this later this semester. And then next one will be called, it is called the contingency table. Right, so contingency table can be two-way table, can be three-way table, can be four-way table, even can be five-way table. Right, so our case is two-way table. We just have these two-way table. All right, and then in default, right, the contingency table will always provide these four things for each cell. The first one is the count, right, which is our observed count, which is 212 for the first cell, right? And then next one is called the total percentage. So what does this total percentage mean? It means they based on the total counts, right? So based on the overall total, what is the percentage of this cell? So that means will be 212 divided by 2,201, right? You will get 9.63% of this cell. Right? So of all the passengers, right, I will have 9.63% of them will be in crew class and alive. Right. Next one, column percentage. So what is this column percentage? That means based on this column, just to focus on the crew class. Within the crew class, what is the percentage of alive of the first cell? So that will be 212 divided by the total for the crew class, which is 850. So you will get 23.95%. This is the column percentage. And then next one, which is the row percentage, right? So what is the row percentage? That means we just focus on the first row, and within all the alive cases, how many of them will be in the crew class? Will be 212 divided by 710, and then you get 29.86%. All right, so it looks like without this, except this count, these 3% are not useful for our hypothesis test, right? They may be useful in in later this semester, but now, for now, they are not very useful. So that means I don't want these information. I can click this red triangle here, right? And then I want to keep this count. I want to uncheck this total percentage, right? Then the total percentage will disappear. And then next one, I don't want this column percentage. I don't want this row percentage, right? Just to keep the counts. Now this is exactly the same table, the same two-way table as what we have in the example, right? And then there are many other options, right? So you can ask it to calculate the expected counts, right? So if I check this, it will show you this is the observed count, and next one will be the expected counts, right? So if you want to make the comparison, right? So for the first one, 212, the expected counts that we calculate is 285.48. Exactly the same, right? Next one, 202, which is 104.84, so which is this expected count, right? So then you even can ask the JUMP to calculate the observed minus the expected, which is their deviation, right? So if you check that, it will tell you the observed minus the expected, which is negative 73.484. Right? So this is the contingency table. Can help you to calculate something, right? Some expected counts. Right, and then the end of this output will be very, very useful, right? It will be the test, right? Our hypothesis test, right? We have two tests here. Right? One is called the likelihood ratio test. Next one is the Pearson test. What we used is the Pearson test, Pearson chi-square test. Right, so this Pearson chi-square test will test the relationship whether they are independent of each other. So the Pearson chi-square test is our independence test, right? And then we have what? We have the chi-square test statistics 187.79, right? Which is exactly the same with our calculation, right? And also you have the corresponding p-value here. Right, so that means based on the JUMP, you kind of can get the results for the chi-square test. But before you can use this JUMP function, you always need to know what is going on inside, right? So you need to calculate, you can understand it and calculate all of these things by hand, right? So that once you have any software, you can just know what is going on, right? And what value do you need to use to make your conclusion. All right, so that will be it for this chapter, and then the rest 10 minutes I want to talk about your exam 1.